So today's speaker is Anindita Bhattacharya. I hope I said it right. The
Yes, you did.
PhD, thank you. She's a PhD student at the Indian Institute of Technology, Kharagpur, and she's going to talk about modulating selective enrichment and depletion of ions using electrorheological fluids in variable area microchannels. So, Anindita, but before you start telling more about electrological fluids, can you maybe tell us more about your background and how did you come up doing your PhD at the Indian Institute of Technology?
Hi, yes. So my background was in I did my BTech in aerospace engineering, and I worked in computational fluid mechanics in my BTech project. Then I went for my master's at ETH Zurich, where I worked on mechanical engineering, energy flows, and processes. And that is how I developed more skills in computational fluid dynamics. And then I started my PhD. Started working in microfluidics and basically new computational and computation methods to work in microfluidics. So th- that is my background.
Nice. Okay. Well, thank you. And you can now start sharing your screen. You should be able to do so queuing my presentation.
Yes, I think I can share my screen.
Yeah. Okay, here we are. That's great.
Yes.
Okay, so people, if you have questions, please do so. Please ask them during the talk if you like. Otherwise, we will do a question and answers at the end, of course. And raise your hand or speak up. That's always welcome. So please, Anita, the floor is yours.
Yes. So, what is ion concentration polarization? Ion concentration polarization, or ICP, refers to the phenomenon where selective ion transport driven by an electric field creates a gradient in ion concentration near the channel walls at the microchannel nanochannel interface. This leads to ion depletion in some regions and ion enrichment in others. So we can see a channel with a microchannel, which then the depth is reduced to get into a nanochannel architecture. And this geometry gives rise to a depletion shock here and an enrichment shock here. So, what is the need for this technology? The role of electromechanics in ICP continues to be emphasized in literature. The role of constitution of the ionic medium remains to be relatively less explored. In reality, however, several applications in microfluidics, typically those involving bioanalytes, concern complex fluids such as blood, saliva, nucleic acid, and polymer solutions, all complex fluids, underpinning the critical role of the fluid rheology on the selective segregation of the target analytes. Recognizing the importance of rheology, recent results explicated the role of viscoelastic fluids on the ICP phenomenon in a charged cylindrical nanopore. So, to increase one further level of complexity, the complex rheology can also depend upon the local electric field itself explicitly. Such cases might occur for electrorheological fluids, typically constituting of a non-conducting medium having suspended particles. So, what is electrorheological fluids? Electrorheological or ER fluids whose rheological properties change under the influence of an electrical field are today gaining attention for separation applications due to their tunable and reversible nature. When subjected to an electric field, ER fluids form particle chains or networks aligned with the field lines. This structural change can trap or segregate undesired particles within a fluid mixture. The properties are being utilized in various applications such as water treatment to remove suspended particles or contaminants and industrial processes for extracting solid impurities from oils or other fluids.
Anita, maybe you want to put it in the present mode so that we can see like your equations and the graphs and so on, just in like big presentation mode. If you can do that.
This one?
Yeah. Thank you. Perfect.
Yeah.
Thank you.
Thank you. The model system. So fluid flow, we consider a model setup featuring a series of variable area coaxial microchannels in which an electric field E1 acts along the channel axis X1. The channels having charged walls resulting from electric double layer phenomenon transports the steady flow of an incompressible ER fluid containing ionic species. Further, the transverse length scale of the channel is considered to be small as compared to the axial length scale, so that unidirectional fluid flow and ion transport may be assumed. The dominant component of the fluid velocity in the x1 direction is thus governed by the following equation expressed in the Cartesian index notation. This is the equation which describes it, where del P del X is the axial pressure gradient. Here it is induced because of geometrical discontinuities in the flow domain as opposed to being applied externally in a pressure driven flow. Tau ij is the relevant, the deviatoric stress tensor component, and rho e is the volumetric density of the free charges in the solution. Following Rajagopal and Weinman, the stress tensor of the fluid flow can be described as given in this equation, where tau is a function of pressure alpha 1 E cross E plus alpha 2 D plus alpha 3 D square plus alpha 4 D E cross E plus alpha E cross D E plus alpha 5 D square E cross E plus E cross D square E. So here tau is the stress tensor, I is the identity tensor, D equals to half plus L is the stretching tensor defined in terms of the velocity gradient L, and the electric field is E. From this equation, we get the scalar P, scalar indeterminate pressure equivalent to the hydrostatic stress that arises from the incompressibility criterion of the fluid. And then we have I1 is equals to trace of E cross E, I2 is equal to trace of D square, I3 is trace of D3, I4 is trace of D E cross E, and I5 is trace of D square E cross E. The resultant configuration enables describing the electric field vector as E equals to E1 small e1, where small e1 is in the direction of x1, plus e2 small e2, where e2 is the small direction is in the direction of x2. The fluid velocity for unidirectional flow is given as u, which is a function of x2 but in the direction of e1. The flow is incompressible so that the trace of d is 0. The stress tensor may thus be expressed in Cartesian notation, which is given, these two equations in Cartesian notation gives rise to these two equations. So using this notation and you considering x2 as y and u1 is u2, one can approximately write it like this, which is a condensed form. So now we consider E naught and theta to denote the magnitude of the resultant electric field and its angle with the x-axis respectively. Then E1 is equal to E naught cos theta and E2 is equal to E naught sin theta. Then this equation, the tau I2 can be written like this using this E naught and sin theta expressions. And then also alpha I can be written as the different invariants of the stress tensor. Then tau I2 can be composed written as alpha prime E1 E2 plus mu prime E naught square del U del y whole square del U del y, where mu prime is effective viscosity, alpha prime is constant, and E1 equal to E naught cos theta, E2 equal to E sin theta. This first term in the right hand side indicates that the fluid experiences an electrorheological body force in the longitudinal direction as a result of spontaneously generated transverse electric field, indicating that a non-zero shear rate occurs even in the absence of externally applied shear stress. It is the fact that only the invariant may be non-positive, in particular to a response to a flow reversal when the velocity gradient changes its sign. Moreover, the direction of E does not influence the flow rheology, which remains sensitive to the square of E alone. So thus, with the ER effects incorporated, one may arrive at the modified Bingham equation, which is given by this formula. So now setting tau, this was the first fluid flow formula we had. We ignored tau I11 del x1 in compared to like the longitudinal stress is ignored compared to the transverse stress, and then we get this equation del tau I12 del x2 plus del p del x1 plus rho e1 equals to 0.
So, Anindita, can I ask a question?
Yes.
From the previous page. So in the expression of tau 1, 2, like tau 1, 1, tau 2, 2, these are basically the diagonal component of the stress tensor, and tau 1, 2 is the off diagonal. I think tau 1, 2 and tau 2, 1, they are same, right? Like
yes.
Right. Yes. So this tau 1, 2 expression in the, I think in the next page maybe, where you have the third bracket of E0 is what is that third bracket? Is it basically the inner?
It is a function of. It is a function of.
Oh, it's a function of. Okay. I was thinking in some kind of inner product or something. Okay.
No. There's a comma there, not an inner product. Hello?
Yeah. Understood.
So with further assumptions that del P del x1 does not vary along x2 direction and the ideals are thin, so that rho E1 is invariant along x2 in the bulk fluid except for a vanishingly thin wall layer, this equation may be integrated as with respect to x2 to yield tau 1 2 is kx2 plus k star, where k is del P del x1 minus rho E1 and c is a constant of integration, may be a function of x1. We next introduce the non-dimensional coordinate y star as y divided by h by 2, where x2 is equals to y. So now we put the boundary conditions at h by 2 and minus h by 2, where u is defined as 0 at the two boundaries. We next consider two examples to illustrate the nature of the fluid flow in a couple of special scenarios. The reason for selecting the two examples is to illustrate the essential physics of interest through a simplified model, striking a balance between the mathematical details and the exclusive implications of electrorheology on the electrokinetic solid transport mechanisms. So the first we have is tau 1, 2. We already have seen this equation before, where alpha depends on E naught square. So equating kx2 plus k star with this, we get k star is equals to a E naught square sine 2 phi, and kx2 is mu, which is a function of E naught square, and gamma square gamma. This implies that gamma x2 is an odd function of x2. Integrating the shear stress distribution at the upper and the lower boundaries can be expressed as a E naught square sine 2 phi plus minus kh by 2, which is of clearly different magnitudes as opposed to the antisymmetry of gamma. For the second example, we see this expression of tau and 2, which has already been defined before here. We use this expression of tau and 2. And we put b hat, which can either be b plus when gamma sine 2 phi is more than equal to 0, or b minus when gamma sine 2 phi is less than 0, where b plus and b minus depends only on E naught square. If phi is 0, which has the same rheological consequence as E1 equal to 0, the above equation reduces to this. This resembles the form tau 1 2 is equal to tau E effective plus eta y, where tau E effective depends on gamma square. Now, for obtaining the flow field of a general scenario with the full influence of both the terms on the right-hand side, we can equate it and normalize it to yield this equation. this kh by 2 plus k star is equals to the the model for electrorheological fluid that we have, and U can be obtained by integration of gamma, which is a function of all this as we have described before. And to obtain k star, we take a definite integral and equate it to 0 because U is 0 in both the lower and the upper boundaries. Now, area averaged model. For the ith ionic species, the transport phenomenon is given by this equation, where Ui, μi, Zi, and Di represent the concentration, mobility, velocity, and diffusion coefficients of the ith ionic species respectively. U is the velocity vector and F is the Faraday coefficient. We consider a binary charge solute system where the individual constituents are represented by subscripts 1 and 2. For simplicity in the calculations, without compromising the central physical theme of our work, we consider a slit parallel plate microchannel for which the lateral width is much larger as compared to the depth of the plane of flow. Thus, the area averaging of the transport equation effectively concerns averaging over the channel depth. Accordingly, for each of these two ionic species, this equation may be integrated over the channel depth along the y direction to arrive at the area averaged forms, which is given by these two equations. The transverse diffusion flux of the ionic species in the y direction is given by di del cy dy, and the corresponding electromigration flux is also given by di del psi del y Zi E psi 1 by kBt, which is the potential induced due to ideal phenomenon, and Zi is the valency of the ionic species. The ideal potential field obeys the Poisson-Boltzmann equation, physically represented by the Gauss's law, which is given by this equation, where lambda is the Debye length and sigma star is the normalized surface charge. This is the normalized boundary condition where potential at the psi star is the potential, and this is related to the surface charge. We arrive at this definition neglecting finite ion size, ion-ion correlations, continuum dielectric assumption, ion specificity, and non-equilibrium dynamics. Finite ion size, the PB model treats ions as point charges, neglecting their finite size. At high concentrations or near highly charged surfaces, steric repulsion limits the number of ions in the electric double layer. The saturation of ionic density leads to nonlinear deviations from PB predicted distributions. Ion-ion correlations. The PB model assumes ions are non-correlated. However, at high ionic strength or in solvents with low dielectric constants, ion-ion correlations become significant. Counter-ion attractions can form structured layers and cause oscillatory charge distributions near surfaces. Continuum dielectric assumption. The PB model assumes the solvent is a uniform dielectric medium, ignoring the finite size of water molecules and their ability to form hydration shells around ions. Near surfaces, viscosity gradients or dielectric inhomogeneities alter ion mobility and distribution. Large or polarizable ions further complicate this by inducing local electric field directions, which the PB model does not account for. Ion specificity. The PB model treats ions as identical apart from their charge. In reality, specific ion absorption influenced by ion chemistry and surface interactions can lead to variations in ion distribution as seen in the Hofmeister series effects. Non-equilibrium dynamics. The PB model assumes local equilibrium which may not hold in dynamic or oscillatory environments. For example, alternating current fields or diffusion-limited charge dynamics in dense systems can lead to nonlinear time-dependent effects. So, combining all this, we can write C1 and C2, mean average of C1 and average C2 as a function of C0 and Z2 by Z1, lambda star and sigma star. these satisfy the electroneutrality condition. Z1 C1 plus Z2 C2 satisfies the electric field due to the surface charge density. To isolate the contributions due to pressure driven and electrokinetic components in ion transport, we first express the pressure driven flow components UP as integration of del UP del Y. And so UP can be written as a function of A1, where A1 is a function of YH, KP, K star minus tau naught, eta, tau E, beta hat. Similar to C.
I have a question because I'm not at all in that field. And I just wanted to ask, like, it's maybe a super stupid question. I'm really sorry. But
No,
if
it's
I
fine.
understood very well, you have a model that describe how the ions are transporting in a microchannel,
Yes.
depending on the electrical field and so on. And there is many equations that I'm so sorry. I'm
It's
trying
fine. It's fine.
my
There
best
are
to
too many
understand.
equations.
But how does the ion transportation works with the change of the microchannel size and area, like roughly the
Yes,
idea?
yes. That
Just
we
to
can go
understand
through
how it
here.
goes.
Here we can see that we are averaging over the depth, and for each, so if we like, if I show you the, yes. So when we are averaging over the depth in each part of where the h is constant, we have the
Yeah.
equation is valid. When the h changes, then we have to recalculate the fluxes.
Okay. And how does the those ions, like they're just doing a pressure driven flow. So whenever you
This
turn
is not
on
a pressure driven flow. This is an electric field driven flow. The
just
pressure
electric. Okay.
the pressure changes come at the interfaces when the fluid velocity changes because of the change in geometrical area, then we
Yeah.
have a pressure gradient to balance it.
Okay. Okay. I need to listen a bit more to try to understand what is happening. But thank you.
You can ask more questions.
For now, it's kind of okay. I understood more or less like what you're modeling. It's just also to maybe you're also working with some people that are doing experiments. I don't know. Maybe it's later in your talk. I'm sorry.
Yes,
But
yes.
it's to understand like how it works, because I'm really like working with viscoelastic fluids and I'm not at all doing that. So I just wanted to understand how it works in those aspect ratio, where the aspect ratio plays a role in your flow, and how
So the
you take it
aspect
into
ratio
account.
plays a role. The aspect ratio induces a pressure gradient and a
Okay.
backflow. So when
Okay.
the fluid is going from a high area to a lower area, then there is a pressure gradient that gives rise to a fluid in the backward direction, which gives rise to a vorticity.
Okay.
Okay, so
Okay.
yes, so
Yeah, you can continue. Sorry.
yeah, it's fine. So here UP can be written as a function of A3. Similarly, C1 tilde P and C2 tilde P can be written as functions of A6, A7, and C0. Then UE, the electroosmotic flow velocity, can be written as a function of A9. C1E as a function of A10 and C2E as a function of A11. So the combined pressure driven and electrokinetic flow velocity satisfies the incompressibility condition, which is this del del x of HUP plus HUV equals to 0. So computing everything, we get one-dimensional unsteady advection diffusion equation of the form C1 del del T of HC0 plus C2 del del x of HC0 equal to C3 del del x of the diffusion term. So where C1, C2, C3 are parametric functions, and the functions C1, C2, C3 are evaluated numerically from a lookup table, And then this equation is numerically solved by a sixth order compact difference scheme in space and a fourth order Ranjit-Kutta scheme in time. Then we move on to the full-scale numerical method. In order to assess the efficacy of our area averaged approach, we also execute full-scale self-consistent finite element simulations to obtain the local fluid velocity at point U, the respective ionic concentrations at CI, the electric field phi. In this approach, the mass conservation equations of the respective ions and the Navier equation were coupled using the Poisson-Nernst-Planck models to arrive at the numerical solutions of the field variables in the 2D space. The conservation equation for the ionic species is del C del T is equals to the gradient of Ji, where Ji is the ionic flux due to combined effects of advection, diffusion, and electromigration. The velocity field is obtained by using the electrological fluid viscosity equation and finally the momentum equation is used. Notably, there is no applied pressure gradient. This is an electric field driven flow. Gradient of P between the ends of the channel, a pressure gradient gets induced to ensure flow continuity amidst the varying cross-sectional area. This is what you are asking. A closure to the problem is obtained by relating the charge density with the electric potential by means of the Poisson equation. So, this is the Poisson equation where rho E is given by this addition of the charges and concentration. So the numerical simulations are executed using the commercially available finite element software ComSolve Multiphysics 5.6b by combining three distinct modules. The electrostatics module is utilized for resolving the distribution of electric potential. The transport of dilute species module is utilized to resolve the distribution of the C0 concentration. The laminar flow module is used to resolve the velocity distribution. A time-dependent solver is employed following the automatic highly nonlinear Newton method with a relative convergence tolerate limits of 10 to the power minus 6. Grid independence tests are conducted for all simulations to verify numerical convergence. So this is the illustration for converging diverging microchannels. This is the anode and cathode, and this is divided into 5 parts. This is the wide microchannel. Then this is a constriction. This is a narrow microchannel. This is an expansion, and this is again the wide microchannel. We make further simplifications by modeling the EDS charge distribution across the channel depth as delta functions at the walls and substitute uniform functions across the channel cross-section for concentration profiles. So C1x is given by a constant C0x and a delta function at hx plus 2 and y minus hx by 2. C2x is also given by a constant function, Z1 over Z2 of C0x. Similar to the case of the governing differential equation, the expression can can also be written like this. This is the time derivative term. This is the advection term. This is the diffusive term. And for further simplifications of the model, if we subtract C1 minus C2, we get this. And so finally, we come to the results and discussions. So here in figure 2, we plot the axial variations in C star, which is normalized C0 along the channel length for H star is equals to 1. As a representative physical scenario, we consider Z2 by Z1 equals to -1, C0 equal to 0.01 moles per liter, implying the debye length lambda is 3.2 nanometers, which when normalized with respect to a typical channel height of 50 nanometers gives lambda star equal to 0.000064. To depict the electrorheology of the fluid, we take eta equals to 0.1 Pascal second, sigma star is equals to 5 into 10 to the power 8. Considering, and we also take the tau E is equals to CE squared, where C is 2.5 into 10 to the power minus 10 Newton per volt, and E1 equals to 4 kilovolt per millimeter. The physical configurations consists of flow between two infinite flat plates. one fixed and raised to a potential, the other being grounded and moving with constant speed. Figure 2 reveals that the region around the deep to shallow junction acts as a species depletion zone, while that around shallow to deep junction acts as the enrichment zone. In ER fluids, the velocity profile has a plug flow region, but the velocity is constant across the cross section. The region outside the plug flow is very narrow in case of ER fluids, leading to very high shear stresses. This causes a decrease in the effective viscosity of ER fluids, leading to very pronounced depletion and enrichment zones as compared to Newtonian fluids. As the Peclet is increased from 2 to 20, diffusion is suppressed, leading to more pronounced ion depletion and enrichment zone. In the case of Peclet number equals to 2, the concentration profiles are more homogenized. If H star is increased from 1 to 100, keeping all the parameters unaltered, the shear rates in the shallow channel increase. With increasing shear rate, the structure breaks down to the particle alignment is overcome, leading to shear thinning behavior of the ER fluid. The reduced viscosity increases the axial concentration gradients and makes the locally enriched and depleted ion concentration regions more pronounced. In all these regions, the area average model gives reasonably accurate predictions as compared to full-scale numerical model, despite the loss in the resolution in the transverse directions. This is figure 3, C star versus X star characteristics of fluids having different constitutive behaviors. The Newtonian fluid has a viscosity of 0.1 Pascal second. The other properties are taken to construct the figures are given in the main text. Figure 3 shows the difference in ion concentration polarization between ER fluids and non-ER fluids. The ER fluid has more pronounced enrichment zone as compared to non-ER fluids. In figure 4, the concentration of the reservoir deep microchannels is varied. For greater concentration of the solution, the EDL becomes thinner, leading to large shear rates within the same for the same bulk flow velocity. The enhanced shear rate breaks up the particle chaining in ER fluid, reducing the effective viscosity and augmenting the shear thinning nature. This reduced viscosity helps to create larger axial concentration gradients and hence more pronounced depletion and enrichment zones. Figure 5 depicts the steady state concentration profiles for different values of eta. As eta increases, the fluid becomes more viscous and the concentration gradient becomes smaller. Consequently, less pronounced will be the depletion and enrichment zone as compared to Newtonian fluids. Figure 6 depicts axial concentration profiles for different values of B. The higher the value of B, the higher the viscosity of the fluid will be. Consequently, less pronounced will be the depletion and enrichment zones as compared to Newtonian fluids. Figure 7 depicts the axial concentration profiles for different values of E1. As E1 increases for the ER fluids, the particles get chained up more strongly and the effective viscosity increases, leading to more homogeneous ICP profiles. For Newtonian fluids, as E1 increases, the electroosmotic velocity increases, giving rise to large shear rates and more pronounced ICP. We next quantify an index of improvement of performance defined as the ratio of maximum concentrations for electrorheological and non-electrorheological fluids. Our results reveal a twofold increase in maximum concentration when electrorheological fluid is used, justifying its use in practice. Figure 8 depicts the axial concentration profiles for different values of sigma star. As sigma star increases for ER fluids, the particles get chained up more strongly and the effective viscosity increases, leading to more homogeneous ICP profiles. For Newtonian fluids, as sigma star increases, the Dukhin number increases, increasing the selectivity of the shallow channel and making the ICP non-propagating from propagating. Non-propagating shocks, sudden jump in concentrations means shocks stay fixed exactly where they are formed. Propagating shocks move towards anode or cathode depending on the value of I star and concentration in the depletion and enrichment zones. So for further simplifications to unveil the importance of rheology towards dictating the feature of shockwave-like propagating phenomenon, we put A6, A7, A10, A11, F1, F2 equals to 1. So which means we have all the concentrations C1, C2, C1P, C2P, C1E, C2E are all equal. In that case, we can calculate the electric field as a function of I and these variables. So then the main equation reduces to this. This is the advective term and this is the diffusive term. So assuming constant wall charge and the reference scale depth of href, this can be normalized. To get this equation, we consider href as the height of the shallow channel so that h star is greater than unity. We next define c star and I star like this. And then this is the equation. The coefficient of the convective component of the ionic flux is this 1 minus h star I star by h star c star plus 1 whole square. And this represents the normalized characteristic speed of the ionic advection. So this the sign of U star determines the direction of travel of the concentration perturbation stemming from alterations in the transport parameters on account of the jump discontinuities at different sections of the channel. The characteristic velocity, which is U star, is a monotonically increasing function of the concentration which asymptotes to unity at very high concentration values. However, for moderate concentrations, negative values of U star are possible. The onset condition of turnaround region of the sign of the characteristic velocity corresponds to the critical condition given by U star is equals to 0. Correspondingly, we term instances of positive U star as supercritical and negative U star as subcritical conditions. The manner in which U star depends on the ionic concentration is strongly dictated by the rheology of the fluid. Prominent ER effects leads to higher viscous stresses and thus less Q. This in turn enhances the value of I star for ER fluids. Moreover, for ER fluids, the shear stresses outside the plug flow region are greater than for Newtonian fluids, making the ICP effects more pronounced. In the depletion region, the ER fluid has less solute concentration as compared to Newtonian fluid. Cumulatively, this implies that U star is lower in the depletion region for ER fluids than Newtonian fluids. On the flip side, in the enrichment region, the solute concentration is more for the ER fluid than Newtonian fluids, which tends to counterbalance the reduction in U star due to high I star. This counteracting influence gets more prominent at high concentration values for which the ER and Newtonian characteristic speeds tend to merge. So here, at high concentrations, U star for Newtonian and ER fluids continue to merge. They show quite difference in lower concentrations, where the U star for ER fluid is lower than for Newtonian fluid. Concentration shock waves is when the left hand side of the equation is equal to the right hand side of the left hand side is equal to the right hand side of this equation, and refers to a sudden and significant jump in the concentration of a solute within a fluid, often resulting from abrupt release or injection of solute in the system. This phenomenon can create a high concentration front pulse that moves through the fluid. In the present scenario, concentration shock waves can form because of nonlinearity of the propagation phenomenon as presented. Physically, this region upstream of the shock has higher concentration than region downstream. Consequently, the region upstream has higher characteristic speeds. For shock to physically occur, the upstream and downstream characteristics have to intersect. In the event of occurrence of the shock, U upstream is greater than U downstream, and expansion shock would otherwise occur. Correspondingly, concentration upstream is greater than concentration downstream is a prerequisite for the appearance of a shock. A stronger and thinner shock is produced when there is greater disparity between the upstream and downstream concentrations. When the values sufficiently close to each other, V star is almost equal to 1. This implies that the shock will travel merely at the speed of bulk flow, restraining its impact to remain mild. In the scenario in which concentration downstream is significantly less than unity and concentration upstream is of order unity, downstream may get negative, manifesting severe shock. The corresponding characteristic speed reads V star is equal to 1 minus I star by Cu star multiplied by H star Cd star plus 1. For sufficiently small CD star, the concentration shock can propagate upstream. The strong shocks can occur in ICP depletion zones. This is analogous to shocks in compressible flows in converging diverging channels, where the diverging part is supersonic, the throat is sonic, and the convergence section is subsonic. The manner in which V star depends on the ionic concentration is strongly dictated by the rheology of the fluid. Prominent ER effects leads to higher viscous stresses and thus less Q. This in turn enhances the value of I star for ER fluids. In ER fluids, the shear stresses outside the central flow region are higher compared to Newtonian fluids, which amplifies the ICP effects. In the depletion region, ER fluids exhibit lower solid concentration than Newtonian fluids, while in enrichment regions, the ER fluids have higher solid concentrations. Nevertheless, the influence of C upstream is overshadowed by the effects of C downstream, resulting in smaller values of I star and V star for ER fluids than for Newtonian fluids. So these are the startup and transient dynamics. We see that gradually at T star is equal to 64, there is a depletion zone and there is a strong enrichment zone. This is the value of U star versus X as for startup. Also, as it reaches steady state, that is T is equal to 64, we get a depletion zone and a strong enrichment zone. Finally, we come to conclusions. We demonstrated the effect of electrorheology on ICP phenomenon in variable area channels subjected to electrokinetic interactions by developing a computationally efficient area average model. Unlike previous studies on ICP, we considered the interplay of axial variations in the induced potential field due to channel height modulation and spatial variations in viscous stresses resulting from combined alterations in the rate of deformation and the local electric field. This confluence culminated in selectively ion-enriched and ion-depletion regions within a variable area conduit. The ER effect was shown to magnify the concentration peak in the enrichment region and valley in the depletion region. Our results reveal that when shear rates are low, the increased effective viscosity for the ER fluids can smoothen out local concentration gradients to result in a more diffuse ICP profile than for Newtonian fluid. On assessing the interplay of various parameters controlling the ICP phenomenon, we can draw the following inferences. For channels having larger deep to shallow section height ratios, greater solid concentrations, lower values of more prominent ion depletion and enrichment zones can be observed, where the ER fluid turns out to be instrumental in magnifying the solute enrichment and depletion effects in the respective zones. Physically, to achieve a higher concentration of the solution, the ideal would become narrower, resulting in increased shear rates at a constant bulk flow velocity. This shear thinning characteristic diminishes the viscosity, facilitating the formation of more significant axial concentration gradients and consequently more distinct depletion and enrichment zones. As eta rises, the effective viscosity of the fluid increases, resulting in diminished concentration gradients. As a result, the depletion and enrichment zones would be less contrasting than observed in Newtonian fluids. The greater the value of B, the higher the viscosity of the fluid. As a result, the depletion and enrichment zones will be less dramatic than those observed in Newtonian fluids. As escalates for ER fluids, the particles become more tightly interconnected, resulting in increased viscosity and producing more uniform ICP profiles. In Newtonian fluids, an increase in electric field results in elevated electroosmotic velocity, leading to greater shear rates and more significant ICP. As sigma increases, the particles become more tightly interconnected, resulting in an increase in effective viscosity, thereby producing more uniform ICP profiles. For Newtonian fluids, a rise in sigma results in higher Duycken number, enhancing the selectivity of the shallow channel and causing the ICP to transition from propagating to non-propagating mode. The constitutive behavior of the fluid significantly affects the velocity of the concentration shock propagation. For the earth fluids, the shock wave at the depletion region propagates at a reduced velocity. Conversely, in the enrichment area, the velocity of shock propagation is contingent upon relative dominance of the parameters. These effects may potentially harness to impose precise control over the local concentration profiles, bearing critical implications in separation sciences and sensing technologies. The selective enrichment at preferential locations within the channel, in particular, may be exploited to pre-concentrate samples so as to amplify the concentration signals. This opens up the possibility of attaining ultra-high sensitivity in analyte detection or rapid biosensing platforms, a capability not previously achieved. So that is the end of my presentation.
Thank you. Thank you so much, Anindita. Do we have any questions from the audience? I just have maybe a couple of very, you actually said it at some point, but I couldn't really get it. What's the typical channel height? I think you said
50 micrometers.
50 micrometers, right? Okay, that's what I got. We also, okay, so we do have a question from the chat. In your simulations, do you see an accumulation of charge on the channel walls?
Yes, there is an accumulation of, no, there is no accumulation of charge, there is accumulation of ions.
Okay. And Jose, please.
Hi everyone, can you hear me?
Yes, yes.
Okay, thank you. Thank you, Anindita, for your talk. I have a curiosity because when you are modeling the ER fluid in COMSOL, I guess that well, the ER fluids, they have a yield stress when you expose them to an electric field, right? So
Yes.
my question is, do you have modeled that yield stress in COMSOL when you are using
Yes, yield stress, the yield stress, this component is the yield stress. Let me show it to you. This A square sine 2 phi, this is the yield stress component.
But how have you modeled or how have you introduced those terms
this expression
in COMSOL?
A square sine 2 phi, this is the Bingham model for the ER fluid, and this is the yield stress.
All right, but let's say that
so
part
I have
in
modeled
COMSOL.
the tau I2.
Okay. And did you have any problem regarding the small shear rate that COMSOL returns to
I
you?
have used moderate shear rates. I haven't used very small or very high shear rates.
Okay. I have more questions. Can I?
Yeah, please.
Sure, go ahead.
Sure. So it's another curiosity. It's about the mesh you have used in COMSOL. Did you take into account? Let me switch this. Did you take into account if there is a high gradient in the velocities close to the walls, or the mesh
Yes,
is regular?
the mesh near the walls have been made very small, the mesh sizes.
And my last question, I think it's there is a slide where you have a sketch, let's say the three models in COMSOL, laminar flow.
Yes, the electrostatics
the
module and the transport of dilute species module.
Exactly. Have you coupled those models, or
yes,
are
I have
they...
coupled those models. Yes.
Can you let's say make a brief summary on how have you coupled
So,
those two?
see, this this is the transport of dilute species model uses this equation. This U comes from the laminar flow model, and the phi comes from the electrostatic model.
Mhm. Okay, and those terms returns a new JI, right? The left side of that
The
equation.
JI, yes, the flux, ionic flux.
And this JI, how it is how does it affect the potential and the velocity of the models, let's say, to
JI impacts the concentration. JI has velocity and potential here. This is the laminar flow velocity. This is the advection, and this is the electromigration, which has potential. These two terms affect the JI, and JI impacts the concentration.
Okay. Okay, so I think it's all from my side. Thank you. Thanks a lot.
Thank you, Jose, for these questions. Do we have any other questions? Okay, well, if not, I'm going to stop the recording here.